So the job for today is for me to teach you to integrate rather deeper than you did that at school. And there are two reasons for that. A, integration is absolutely central to what you will be doing in your second and third years. And B, unlike the differentiation operation, which was largely mechanical, you simply had to memorize the rules, and you've done that quite well by now, and just crack on. So in principle, you can train a mechanism or a program to do differentiation. Unlike all of that, integration is not a process for which a universal algorithm exists. That is to say, integration is an art, and rather a lot depends on your experience, on your knowledge of how it functions, on your ability to do so. And so, not for all elementary functions and their combinations, a finite-sized expression for an integral actually exists. And you'll see a few examples in your workshops. And so today we will go through various methods of integration in the roughly the order of difficulty, and then the subsequent lecture will be about the various transformations that you can have under the integral in order to simplify the process. Okay, so at a very basic level, there is a table which is similar to the table that you have for derivatives, which at the level of that table, for the small elementary functions that there are, you simply have to memorize. And I'm pretty sure you've done that already. So if we plot the function in here, that's our derivatives, and that's our integrals of x and dx. Then the basic table can be simply built by reversing the differentiation to ask ourselves which function must we differentiate in order to get our function back. So if we look at basic things like x to the n powers, you know that the derivative is x minus 1. And so if we ask ourselves, okay, what is the corresponding integral whose derivative x to the n is? Well, clearly it has to be x to the n plus 1, because we will subtract 1 when we are differentiating, and then this n plus 1 will pop out in front, so we need to divide this away. N plus 1. And then if we differentiate this, we will get x to the n back. Then of course the exponential doesn't change, so not forgetting the constants in here. E to the x, the derivative is e to the x, and the integral is e to the x plus the constant. And the constants are always here, because for differential equations, as you saw, they have a physical meaning, and for the integral in here, because the constant vanishes on differentiation, there are many possible integrals for a given function. And so on, right, we can go to something more complicated. Log x, well, derivative, as you know, is 1 over x, but the integral is not obvious. We will get to the corresponding integration techniques in the next lecture. But if we write something like that, we can easily demonstrate by differentiation that that is actually the integral of log. So if we compute the derivative of that, x log x minus x prime, what we will see is here we will have to differentiate this by parts. So it will be log so a prime b plus ab prime plus x over x minus 1, and that's x over x is 1 minus 1. It cancels, so that's actually log x. So this you don't need to memorize, because you will have a technique given to you in the next lecture that actually integrates this logarithm x. I think it can be taken by integration by parts and so on. Okay, so this continues, and there's a minimal table in your handout for these derivatives and integrals, and by the time you've trained your hand sufficiently, you will realize that you actually remember all this. Much like the second years by now probably remember the table of all 20 amino acids. You never thought you actually are going to memorize that, but if I tell you to draw alanine, you probably will. So it is kind of mechanical, and eventually it sediments in your head. Okay, so for more complicated functions, obviously not everything is elementary. There are either complicated combinations of these, or there are functions that are not even in the same class and must be transformed into that class. There are various techniques of integration, and for a couple of them, a geometric interpretation is possible. So let me draw some functions. So that's x, for x, and we'll just draw something like that. And here's, roughly speaking, our integration interval. That's the area we're looking at. So, and we are operating with indefinite integrals here, but we can always put some finite limits on them, and then the geometric interpretation is the area. So the very first thing that occurs for all over the place is something like integral x minus a. That is to say, the function has been shifted right or left by an amount plus minus a. I guess if we've used a and b in here, let's make it alpha and beta. We don't have any notation collision. Well, it stands to reason that if you simply shift your coordinate axis by a certain amount, which this effectively does, the area shouldn't change. It doesn't really matter whether this is from 0 to 1 or from 1 to 2, so long as the function shifts with it. So essentially, by doing this, we are relabeling the axis, but everything else remains the same. And so the integral is actually exactly the same constant as if this a didn't exist. So to give you a simple example of that, if we have an integral 1 over x plus 2 dx, well, we know the integral of 1 over x. That's a logarithm, and if it's x plus 2, we don't care. So that's log x plus 2 plus the constant. So if you see a constant added or subtracted from the integration variable, just proceed as usual. Just remember to keep that constant along with your variable at all times. The second method that again admits a geometric interpretation is when the variable under your integral is multiplied. To integral f of ax dx. Well, this amounts to not shifting your axis, this amounts to rescaling your axis. That is unit transformation. If your axis was originally in meters and you decided to measure it in kilometers, well, obviously there are fewer kilometers than there are meters in any quantity, and so you need to scale your area down. So the result is 1 over k. And it stands to reason because if you start differentiating this back, then of course 1 unit of k will pop out, cancel with this k, and you will get your f back. So I've got an example in your handout, an integral cosine x dx. Well, we know what an integral of a cosine is. It's a sine, and because we have an 8 in here, it's 1/8 sine 8x plus a constant. And again, from your knowledge of how to differentiate, you can immediately tell that this is the right answer. If we start differentiating this, we will get a cosine. The content of the cosine will remain exactly the same, but 1/8 will come out and it will cancel this 8, and so we will have the cosine. So far so good. That's just the shifting and rescaling. And unfortunately, the following properties in your handout do not have simple geometric interpretation, but we can always rely on our understanding of the corresponding properties. So a somewhat obvious observation, which people surprisingly often don't remember when they're actually trying this, is before you integrate, try to simplify what occurs under the integral. We could make it a trick question and just put something horrendous under the integral, which one would no hope of integrating directly, except if one simply just looks at that integrand and realizes that, it all simplifies and collapses and cancels itself and eventually equals 1. So before you are looking to differentiate or integrate, I strongly recommend that you simplify what it is that you are integrating or differentiating. And so, simple trig simplifications. Basic things. I've got a few of them in the handout, but as you know very well from school, the list of trigonometric relations is infinite. I wouldn't say I remember many of them. I think I most just remember the basic expressions for sine 2x and so on. And so if we do require you to use trigonometric simplifications in the integration process, we will provide them. So we emphasize understanding in this course. I don't want you to just plainly memorize anything but the absolutely necessary things. And so all these things will be provided. So basic things like what we're going to use in a moment is, for example, sine x times sine y. There are ways of deriving them, but they're all horrendous and highly technical. We don't really care. Cosine x minus y minus cosine x y, and an infinite number of other expressions. And then, of course, we come across some practical integral of that type, and these integrals are ubiquitous. So, acoustic signal processing, for example, is all about integrating trigonometric functions numerically or analytically. So let's say an integral sine 2x sine 4x dx. And we just simply apply that formula over there. So 1/2 of an integral x minus y will be 2 minus 4, but cosine is an even function, so we don't care about the minus. So cosine 2x minus cosine 6x dx, and all of that comes up. So notice we've got 2 and 6, so we have to use this 1/2 and 1/6 will come out during integration. The integral of a cosine is sine, and so in total we've got 1/2 and then 1/2 sine 2x minus 6 sine 6x as the constant, and we can simplify that and so on. There is a method for trigonometric simplifications that I wouldn't advise you to use routinely, but it is an absolute last resort nuclear option, which is guaranteed to simplify any trigonometric expressions that you have. And that is Euler's formula. I gave it to you already a few lectures ago. E to the I x is cosine x plus I sine x. And in your workshop, you were asked to prove the reverse relationships. You demonstrated that cosine x is e I x plus e minus I x over 2, and sine x plus e I x minus e minus x over 2. Notice that this converts trigonometric expressions into exponentials. Trigonometric functions are hard to multiply, hard to transform, you cannot take the roots of them, and so on. However, exponential functions are trivially easy to multiply, trivially easy to take the powers and roots of, and so on. And if you replace every cosine with that and every sine with this, remembering all the multiples of all the arguments, you would produce a colossal heap of complex exponentials, which will just multiply and collapse into just a few of them. And at the point when you put the final simplified answer, you convert your exponentials back into sines and cosines. The imaginary part will certainly cancel because you start from a real function, which will get the real function out. If it doesn't cancel, check for errors. everywhere. So this simplifies any trigonometric expression. There is, and machine algebra systems, for example, internally never work with trigonometric functions. They work with complex exponentials, but if the user insists on getting the trigonometric functions out, they would oblige to return it. So this is how it's done. So it's a bit of a rigging, right? Don't use it in time-critical situations like the exam, but if you are faced with some horrible trigonometric function, this is how at least a highly efficient computer would simplify it under the bonnet. Okay, now the next topic requires a bit of discussion. So item 4 is substitution. And this is where all those differentials are coming into the picture, and this is why I've spent an entire lecture telling you about differentials, and then we were calculating them at your class. So let's take a look at some standard integral f of x dx. And let us say that f is something horrendous. I mean, we don't have to go really far here. Let's say it's a cosine. But it's a cosine not of just x, but of some function of x. Something like this. X cosine x squared. Well, this is becoming a problem, right? We know how to integrate elementary functions, as the table. We know how to integrate, shifted, scaled, various products, and so on. But here we are seeing a nested function. There's a square inside and a cosine outside. We do know perfectly well how to differentiate these things, but integrating is a much harder proposition. Generally speaking, there's a recipe for this, which very roughly says, take the fragment that annoys you the most and give it a different name. Here the fragment that at least annoys me the most is the square. So I will say y equals x squared. And let's call this substitution. And well, it will become cosine of y, which is marginally easier. It will become root y, which we can hopefully deal with. And then the important thing is when we do this substitution, we must also transform dx. Right? This is the little area element. This is the slice that we had when we defined the integral in here and took the limit, like the limit of an infinitesimal small slice. This is dx, and this is why it appears under this continuous summation sign. And of course, if we are transforming the variable, then the expression for the slice thickness must also be transformed, and that's actually the differential. So, when we are doing such substitutions, we must find not only the relationship between y and x, but also the relationship between dx and dy, which is exactly the differential. So here, dy is 2x dx. You know pretty well how to calculate it, get the derivatives, takes the dx and y. All right, what we now have is we have the expression for y and we have the expression for dx, and we need to replace all of it. So, an integral. Let's just keep this x for a moment because it will cancel. X cosine x squared is y, and then dx is dy over 2x. Y over 2x. Well, great, because x disappears. We could have made it the square root of y, but it would have gone anyway. And we are left with a half integral cosine of y dy, which we know how to take perfectly well. It's a sine. So that's a half sine of x plus of y plus a constant. And the final thing to do in here is to get the y back into x, which is just x squared. And so the answer in here is a half sine x squared plus a constant. And that's our integral. And if we differentiate that thing back, chain rule, so the derivative of the outer function, that's actually the cosine, times the derivative of the inner function, 2x. These two will cancel, and it will leave us with the x. So clearly, we have integrated correctly because the derivative is equal to the expression under the integral. Now, this is where creativity begins. It is not possible in general to even predict whether a particular substitution would result in your integral neatly simplifying like that, or it would make the expression even more horrendous. So what you will have to do and what you will have to practice doing is trying various different substitutions that may or may not work, and you have to be fully prepared to the situation where it doesn't work. So you do the substitution, you go through all of this transformation, and the result is even bigger than the one you started from. Well, oh well, tough luck. Try a different substitution, and this is how the game plays out. So, having been said, there are tables of standard substitutions, and they generally exist in situations where the substitution is completely unknown. And some smart chaps, you know, in the 17th century have devised substitutions to do work in those situations, and a few of them are in your handout. One particular thing that kind of stands to reason once you look at it carefully is something like this. If you have a function of a cosine of x times sine x dx, then this annoyance rule, so to speak, tends to work. What's annoying in here is the fact that cosine occurs under the integral, and so in here, if we say that our y is cosine x, then dy is minus sine x dx. What it does to the integral in here is it becomes f of y times sine x, and dx is dy over minus sine x. Sine cancels, and we are left with minus integral of y dy, which completely eliminates all the trigonometry from here. And the way to see this is to say, well, actually, this sine x dx is a differential. It's minus d of cosine x. And noticing this requires experience. You have to calculate, to have calculated enough differentials in your life to remember that that's the case. So this is a situation where the substitution is kind of visible with the naked eye. Let us go through an example where a substitution is completely obvious and demonstrate. Still, eventually, in that case, we do get the right answer, or at least, well, an answer of sorts. So, an integral dx over 4 plus x squared. Surprisingly enough, if you try attacking this integral directly with elementary functions and powers and so on, no amount of tinkering will help. You will discover that no matter what you try, this just resists. It doesn't match any integration pattern that you know about. And the reason for that, and that is again a result from roughly the 18th century, is the one substitution that works in here is a very strange one. We say that x, so this variable, we will make it equal to 2 tangent of phi. Why would we possibly want to take a nice little elegant fluffy rational expression and convert it into some trigonometric horror? Well, let's try. That is 2 sine x over cosine x. We need not only to put the substitution in there, we also need to replace the differential, so we must calculate the differential. Dx is the derivative of this times, so it should be phi. So derivative of this with respect to phi times d phi, and that is 2 sine phi over cosine phi prime d phi. Derivative of a fraction, so sine prime is a cosine times the denominator, cosine squared phi minus denominator prime times the numerator minus sine times the sine, another minus, plus sine squared phi over cosine squared phi d phi, which makes sense. You do remember that the derivative of a tangent was the second square. So in here is d phi over cosine squared phi. So far so good. Let us now plonk all of that under the integral. So our dx is d phi over cosine squared phi, integral d phi over cosine squared phi. Notice that I'm using d phi as a variable because it is. Back at school you were using it more as a symbol, but it really has got a meaning, so we can move it around the integral. Then this denominator is still there, 1 over 4 plus x squared, so 4 sine squared over cosine squared. Okay, if we now multiply up the denominators, what will happen is this will become 4 sine squared, this will become 4 sine squared. It's an integral d phi 4 cosine squared phi plus 4 sine squared phi. Well, nice, because everything cancels. And we are left with 1 over 4 integral d phi. And I think I lost a factor of 2 somewhere. Yeah, there. It goes in here, and then goes in here, and then goes in there, and then finally here, here. And so that is 1/2 integral d phi. Well, that's a heavily simpler integral, you might agree, compared to what we had originally. So integral d phi is 1/2 phi plus a constant. And finally, what we need to do is to do the backwards substitution. We knew that x is 2 tangent phi. That means that phi is 1/2 tangent x. And that means that that's 1/2 x here. 1/2 arc tangent x over 2 plus that constant. And I'm pretty sure that you've seen this somewhere already, in some textbooks at school or here, and you were wondering why would that integral possibly be the arc tangent, and how can one possibly memorize it? Well, the answer to the second question is one can't possibly memorize this. Doing all these calculations for chemical purposes is my day job, and I still don't remember these integrals. So anything that human cannot realistically remember will, of course, be provided in the exam. But what we do expect you to have is the understanding of how these things came about. So somebody bumped into a rather important integral. It's a Lorentzian function, actually. It occurs in spectroscopy all over the place. Somebody wanted to integrate it, realized they couldn't, scratched their heads long enough. It would have been years back, until they came up with the functions that actually integrates. Okay, so these are substitutions and the example of a substitution. The next fairly complicated thing that you will come across are rational expressions. So various fractions, polynomials, in both the numerator and the denominator. So that would be item 5 on our agenda, rational expressions. Let's say we've got something like this. An integral p of x over q of x dx, where both p and q are polynomials. And more importantly, the highest power in the numerator is smaller than the highest power in the denominator. So a good example would be something like this. Dx over x minus 1, x plus 2. Clearly we have a quadratic function in the denominator. If you just have the quadratic expression in here, find the roots and factorize it into brackets. In the numerator this is just 1, which is the simplest polynomial we can imagine, but it could have been something else. Now again, this I think is the content of the A levels, but I doubt many of you remember it. There are ways of splitting this expression. There's a pretty fundamental theorem in mathematics, in fact, that says that an expression of this type, 1 over x minus 1, x plus 2, can always be written in the following form. Some number a, x minus 1, plus some number b, x plus 2. Does this look familiar? You must have spent some time splitting them up. Well, of course, this we don't know how to integrate because it's got a quadratic function in the denominator, but this we do. They're just logarithms. And so integrating rational expressions, therefore, amounts to crushing them down to elementary things like this, and then integrating the little pieces, and they will be logarithms. So to remind you how this is done, we just take the right-hand side and we reassemble it. So we multiply this fraction by x plus 2 and that fraction by x minus 1 at the top and the bottom, and we merge them together. So a x plus 2 over x minus 1 x plus 2, so that's equivalent to the expression here, plus b x minus 1 over x minus 1 x plus 2. So you can see the denominators are now the same, so we can add it up, which is a x plus 2 plus b x minus 1 over x minus 1 x plus 2. And this must be equal to that, so denominators can be removed, and we therefore must have 1 equals a x plus 2 plus b x minus 1. Funnily enough, this is one of those rare cases where one equation for two unknowns is actually uniquely soluble. And there's a different philosophy in here. Let me just transform it a little bit and then I'll walk you through the philosophy. 1 equals a plus b x. So I collected the terms in front of x, plus 2a minus b. Now let us think about this. This must be true for all values of x. So we can write in here for any x. X equals 1, x equals 2, and so on. So this isn't actually one equation. This is in fact an infinite number of equations, because this must hold true whatever value of x we put in there. Let's have a good think. If x is, half a gazillion, the only way that this expression can still continue to equal 1 for any value of x is if it doesn't depend on x. The only way it wouldn't depend on x is if a plus b is 0. Well, if a plus b is 0, then of course 2a minus b must be equal 1. That's our system of two equations for two unknowns. So the secret in here is to observe that all of these relationships must be true for any variable. And then after a bit of philosophy, you get these things. You can also get them by picking two arbitrary values of x, like x equals 1, x equals 2, and then that will give you a different system of equations, but the solutions are going to be the same. So that tells us that a is equal to minus b, and then minus 3b equals 1, and then b is minus 1/3, and a is plus 1/3, and that gets us this factorization in that. Check I haven't made any arithmetical mistakes in the handout. So that is 1/3 of 1 over x minus 1 minus 1 over x plus 2. Can be verified by direct inspection. If we simply put the fractions back together, we should get the original function back. Well, now that we split it up, we can actually integrate it. Let us do it. Integral of that dx is an integral 1/3 of this dx, and that is 1/3 of log x minus 1 minus 1/3 of log x plus 2 plus a constant. Again, the best way to check that you've done your integration correctly is to differentiate back and to make sure that the derivative is equal to the original expression under the integral. Okay, so these are the things you have in one way or another bumped into at school. Let's go into something that you haven't actually seen at school. And that's called parametric differentiation, and that is a simple observation that if a function is well behaved, then differentiation and integration, so long as they happen with respect to different variables, are actually interchangeable. So let's say we have a function, integral f, that depends on a and x, or perhaps y and x. But the integral is only with respect to x. So this integral will be a function of y. If f is continuous and differentiable, memory serves, maybe it has to have a continuous derivative, but essentially if it's sufficiently well behaved, then this dy can be just pulled inside the same as dy dx. What this means that if we have multiple variables and we are only integrating with respect to one, we are at liberty to differentiate with respect to the other, either before or after the integral. So derivatives can be pulled in. What does this mean in practice? Let us consider something that, again, we wouldn't really know immediately on the surface how to integrate x e to the ax dx. If it was just the exponential, well, we would have known how to do it, but it's a product. I will go through the integration by parts in the next lecture, but for now, let's just say we are stuck. What we can actually observe, however, is that this is a derivative of just the exponential with respect to a. If I take that and I differentiate it with respect to a, x will pop out in front. So this is actually an integral of d by dA e to the ax dx. But we are integrating with respect to x and differentiating with respect to a, and the exponential is a very well behaved function, so we can pull that out. So d by dA integral e to the ax dx. Well, that actually is possible to take. We know exactly what the integral is. So that is d by dk of 1 over a e to the ax plus a constant. Philosophy here would preserve this constant through the integration, through differentiation process. So technically speaking, we do get a constant out of the integral, and once we differentiate, that constant is supposed to vanish. But of course, the integral is with respect to a, and so this constant is technically at liberty to depend on a, and essentially what you do is you keep it kicking around somewhere. Because ultimately you've been taking an integral, and once you differentiate that, all constants vanish and so on. So this is a subtle point which we could have gone through in greater technical detail, but we don't really have the time. Just keep the constants around. Well, differentiating this with respect to a is actually quite easy. It's a fraction, so the numerator prime, that's x e to the ax, times the denominator, so a, minus denominator prime times the numerator, just e to the ax, over denominator squared plus the constant. And so you can see it's a fairly complicated function, right, with respect to both x and a, but if we differentiated that with respect to x, we will get this. And more importantly, we have avoided a considerable amount of trouble by recognizing that the integral is a derivative. And this is another example of creative thought. Again, nobody would tell you that, oh, hey, that's a derivative over here. You need to be able to recognize this. And that is, again, experience. And if you've differentiated enough exponentials in your life, you would actually spot it straight away. But it would require. Okay, so the final topic for the first lecture, at least on the integration, is something that you've already glimpsed in your workshops. That is that Taylor series are faithful representations of the original functions. If you differentiate or integrate a Taylor series, you get a derivative or an integral of the Taylor series for what would have been there if you did it to the original function. So let's write a Taylor series for a sine, and then let's just integrate for a cosine. We know that cosine x, after a great deal of trouble, many of you did that quite well, no integral yet, it's a sum from n for a cosine from 0 to infinity, some pretty horrendous Taylor series, minus 1 to the power over k, x to the power 2k over 2k factorial. That was the Taylor series for the cosine, and the more terms you have, the better it starts to approximate in the cosine. And because it has a factorial in the denominator, you may remember those convergence conditions. The convergence radius for this series is infinite, converges everywhere. Okay, let's integrate. Integral cosine x dx is an integral of this thing here. As I told you, integration is a linear operation, so the integral of a sum is the sum of integrals, sum and 0 to infinity integral. Let's pull also the constants out, minus 1 to the k, 2k factorial, and actually integrating a power x to the 2k dx is quite easy. We just wrote it in a table somewhere. So sum n 0 to infinity minus 1 to the power k over 2k factorial, and integral to k x to the 2k dx is x to the 2k plus 1 over 2k plus 1 plus a great number of constants from each of these integral, which we will collect into one big ginormous constant. Well, let's take a look at what we got in here. 2k factorial is 1 times 2 times 3 times 4 all the way to 2k. And now we've got 2k plus 1. So this is actually 2k plus 1 factorial, this entire thing. So that is the sum from m0 to infinity minus 1 to the power k over 2k plus 1 factorial times x to 2k plus 1 plus a constant, which, if memory serves, is actually exactly the Taylor series for the sine. Yeah, my handout says that if you look up the expression for the Taylor series of a sine in a book, you would see that it matches, and that's actually sine x plus a constant as it should be. So let's, to summarize this, Taylor series and polynomial approximations in general inherit the properties of the original functions. Well, quite predictably, right? If you differentiate or integrate them, you get Taylor series for the corresponding derivatives of integrals. This helps in situations where the integral of the original function might not exist, or at least not exist in the finite form. You can hack an approximation together, and you know you are at liberty to differentiate and integrate the resulting approximation, and the approximation will remain valid. Convergence values might change, so check that it still converges. It might not in the points where you're interested in it, but these are technicalities, right? So you can do to Taylor series everything that you would want to do to the original function, and the approximation will preserve itself to some extent. Okay.